Session is a talk by uh, Greg Pearlstein from Texas and Tuscany, who is going to tell us about Archimedean height pairing for higher cycles. Greg?
Okay, thank you very much. So, well, I will join the chorus of people saying that, I really enjoy being in Miami, and I hope that at some point in the not too distant future,
Yeah, yeah.
I can
We
Miami.
will redeem ourselves, I promise.
Yeah, okay.
I,
Yes. All right. And so, all right. So this is joint work with Suvik Goswami and Jose Burgos Gil. And I should say I'm using a document camera. And so uh, I can't see the chat on the Zoom thing. So you have a question, like speak up. If you put it in the chat, I'll see it at the end of the talk or something like that. Okay. And so my thanks to Patrick Brosnan and Matt Kerr and James Lewis. So you can see the screen now I'm about to write. Yes. Okay, so the first part of this is just like some background on Arakelov geometry. Okay, and so this here, we let X be a compact Kähler manifold. We let A and B be analytic cycles. On X, and there are some conditions. So the complex dimension of X has to be the complex dimension of A plus the complex dimension of B plus 1. The second thing is we have to have A and B are homologous to 0. And the third thing is that we want the support of A to intersect the support of B to be the empty set. Okay, and so if we have all of these things, then we can define this height pairing between A and B to be, this is the Archimedean part of the height pairing. I'll say more about that later. This is the integral over A of some A to B, where some A to B is a Green's current. For B. Okay, so now this may take a minute to focus. This thing's a little bit like a frog. It has to see motion. Okay, so the classical examples, if X is a compact Riemann surface, we'll just take A and B to be the difference of pairs of points. Then we take a harmonic function on X minus B, and F has to be asymptotic to log S or minus log S at the 2 points, B plus and B minus, and then this height pairing is just the difference. Okay, so this is what we're going to be thinking about, kind of vast generalizations of this. So any questions on the first page before I go on? Okay. All right, so now there's an alternate approach. So I'll want my X, A, and B as above, then I can find this canonical subquotient. Mixed Hodge structure of H, 2D plus 1, X minus the support of B relative to A, and then Tate twist the whole thing. So it has weights 0, minus 1, and minus 2. And here G is the complex dimension of A. All right, so this MAB, so it has weight graded quotients, Z of 1, Z of 0, and in the middle we just have the cohomology of X. And so this extension class here is fixed by the Abel-Jacobi image of B, or if you're being really fancy, the dual of the Abel-Jacobi image of B. And this part here is being fixed by the Abel-Jacobi image of A. Okay, so I need to move this up. Okay. So over R, okay, so X2 is 0 in the category of mixed Hodge structures. So over R, the remaining data of this mixed Hodge structure is just contained in X1 of the mixed Hodge structures R of 0 by R of 1. And then, so we have a little lemma, which says that if 1 is the generator of Ker W0 and 1 dual is the generator of Ker W minus 2, then this height pairing between A and B is equal to, I take delta of MAB of 1 and I divide it by 1 dual. So here, delta is in the endomorphisms of MAB, which lower the weight filtration by 2. So I take a lift of 1 to here, I apply my delta, that's going to be some multiple of the generator of Ker W minus 2. And this delta is this Deligne splitting of MAB, and I'll say more about that later, but for now, that's all I'm going to say about it. So in other words, there's a very natural way of understanding what this height is in terms of a certain splitting of mixed Hodge structures. So far, so good. I'll then go on to the next page. Okay, so so then we can have the relative version of this. Which thing is not at level? That one, that one. Okay, so the relative version of this. Okay, so now we need a triple X, A, and B as above, but now over some parameter space S. Okay, so I need a family of smooth projective varieties over S. I need these cycles, A and B, homologous to zeros on the fiber, etc., etc. So this gives an admissible variance of mixed Hodge structure V over S, or maybe I'm lying, maybe it's really only over a Zariski open subset of S, but I'm not going to worry about that for now. Okay, so H is the cohomology of X in cohomology of X in degree 2D plus 1, shifted down to have weight minus 1. These are the two pieces before, and then these nu A and nu B are the normal functions of script A and script B. Okay, maybe this one's really the dual of a normal function. Okay, so now what are we going to do? So we can abstract what was written above. Okay, so we're going to be working with H as a weight minus 1 variation of Hodge structure, and everything is polarized or graded polarized. I'm not going to keep saying that. HZ, I'm going to want my local system to be torsion free. I'm using certain duality results. Okay, so the nu corresponds to a short exact sequence of the category of variations of mixed Hodge structure. W also corresponds to one of these short exact sequences. And so at some point you have to prove some gluing lemma that says that you can glue these two things together. But so the definition is if U is an open analytic subset of S, then a bi-extension of type nu omega is a variation of mixed Hodge structure, and later on will require it to be admissible, of V over U, such that it has weight graded quotients. Z of 0 is square root of U0, H, so this is given by nu, and then it also has square root of U minus 2. This will be given by omega, and so this is Z of 1. Okay, now I need to move this up a little bit. Okay, and then B of nu omega U is equal to the isomorphism classes of such. Okay, so basically what I'm saying is that if you give me two normal functions, I get these kind of isomorphism classes of variations. And now to get to the punchline. Okay, so Hain and Reed observed that this B of nu omega, this is an O star torsor, so we can let L be the associated analytic line bundle. So then we'll have this definition. So if nu is an oriented, no, yeah, sorry, there's no if. Okay, wait a second. Okay, fine. If nu is an oriented, I'll explain that later, by extension, variation of mixed Hodge structure, we just define the height of nu to be delta of 1 over 1 dual, where delta is this Deligne splitting. So this is done fiber by fiber. So I mean, if you'd like at S, then I put delta of S there. Okay. So the proposition is that if I define, so these variations of mixed Hodge structure by extension type, they're the sections of my line bundle L. So if I define the, in fact, they're the non-vanishing sections. So if I define the norm of V to be X with minus the height, then this defines a Hermitian metric on L. Okay. So now what do we want? Okay, so now we're going to put S into S bar, normal crossing divisors, etc., etc. I'm going to be assuming unipotent monodromy. That's not strictly necessary, but let's not worry about that. Okay, actually, okay, the unipotent quasi-unipotent, it's okay. Okay, so nu and omega, there'll be admissible normal functions, and then we're going to have to add admissibility to this condition on B of nu and omega. And so our first question, question 1, is does L to S extend to L bar to S bar. And so, I mean, what I really want is that I want this extension L to bar to S bar to have admissible variations of mixed Hodge structure of by extension type as the local non-vanishing sections. Okay. And question 2 would be, does this metric on L extend to L bar? All right, so those are some questions that I'm interested in. And now, let's see. So here I'm not going to try and write, I'm just going to try and discuss. Okay, so this is in my last joint paper with Patrick Brosnan in the Duke Math Journal. So the first one is that there actually is a canonical choice of extension of L to an element like L bar canonical in the Picard group of S bar tensor Q. You have to tensor with Q there because the monodromy might be rational, so you might be adding, a rational number times a boundary divisor, but okay, you can tensor through to clear out that if that's what you're worried about. And that result definitely has nothing to do with quasi-unipotent monodromy. It's perfectly okay for that result. Okay, so the second thing is that, so the existence of singularities of nu in the sense of Green and Griffiths is an obstruction to the extending this metric on L of nu, and you can always dualize it to get a nu dual, and so then you get a bi-extension metric. So singularities in the sense of Green and Griffiths, which are related to the Hodge conjecture, are the obstructions to extending the metric. So in some sense, this is kind of like some Hermitian differential geometric way of thinking about the Hodge conjecture. Okay, so now this is much older result of mine. It was in the Journal of Differential Geometry. I think it's 2006. So this is just the one parameter case. So if I have a bi-extension variation over delta star with unipotent monodromy, then there's always a rational number mu, so height of S is asymptotic to mu times log of absolute value of S. So if I add these two together, I'll get something which is bounded. And in fact, that's what's in this. This again is a result of this relatively recent paper with Patrick Brosnan and the Duke. So the limit as S goes to 0 of the height of S plus mu times the log of this uniform parameter, that's equal to the height that you can construct from the local monodromy, the limit mixed Hodge structure, the limit Hodge filtration F, and the wedge filtration W. And now you might complain that, well, this side over here looks like maybe it depends on the local parameter S, but the choice of local parameter S also determines what the F infinity is that goes here. So, I mean, in the end, this washes out. So you actually do get equality, and it doesn't depend on, well, the value will depend on S, but I mean, the statement being true doesn't depend on the local parameter being used. All right, any questions so far? Because now I'm going to try and start stating the work with Jose and Burgos. Questions on any of this? Okay, well, if not, then we have to go on to the next slide. Okay, so this is joint work with Burgos Gil and Goswami. So the first one is one, constructs Archimedean height pairing. For higher cycles. So higher cycles here means in the sense of Bloch, Bloch's higher child groups. Using invariants of mixed Hodge structures. And two, where possible, extend results from the classical by extension stuff, like what I did with Patrick, to higher cycles. Okay, so those are the goals. Okay, so now I have to tell you about the kind of previous work of just Burgos Gil and Goswami. So this appeared in Advances Math 2019. Okay, so here we're going to let X be a smooth projective variety over C of dimension D. Okay, so X and Y are going to be in these complexes. So the only thing you need to know about these complexes is these are the complexes that these are a set of complexes which compute the higher groups. Okay, so I have my class in this complex, in this part. And of course, I want them to give me cycles. So I want D of Y and D of Z to be 0. And okay, now there are some conditions. So I want that twice P plus Q minus D minus 1 is M plus N. And I want Y and Z to intersect properly. So maybe I should say a little bit about that. So this Bloch complex involves, you look at X cross box N cross box M. So you have projections onto box N and box M, and you have to pull these things back. So this properly intersecting means properly intersecting in here. If you know what that means, I'm probably not telling you too much. Otherwise, this is just a hint at what it means. Okay, and the third condition, which is maybe kind of the major emphasis of doing this project, is they also want the real regulator of Y and the real regulator of Z to be 0. So given those conditions, then there is a kind of, now I'm going to put infinity here because this is the Archimedean part of something much bigger that really is like arithmetic child groups. So this can be defined using green currents. Okay, so so Suvik and Burgos Gil, I mean, they gave this construction, but I mean, it is somewhat restricted by this condition that the real regulators be equal to 0. So if you'd like, our first objective is we want to kind of like remove this. Okay, questions? Comments? Okay. All right, so now let's, next slide. Okay, so now on to heights of mixed Hodge structures. So Deline showed that if you give me a mixed Hodge structure F, W on V, then it has some functorial analog of the usual Hodge decomposition, and this kind of uniquely specified by compatibility with FW and this conjugation action. Okay, so now FW is R split if IPQ bar is IQP. So for pure Hodge structures, these are HPQs, and this is always true. For mixed Hodge structures, this is not true. Okay, so then Deline showed that there exists a unique delta in GLVR intersect direct sum P and Q less than 0 of GLV PQ. Okay, so if you have a mixed Hodge structure on V, you get an mixed Hodge structure on the endomorphisms of V. That's what these GPQs are, such that F hat W, which is e to the minus I delta FW, is R split. Okay, so now this next part is just a little bit of notation. Okay, so if H is a mixed Hodge structure, the max of it is the largest K you can find with ger K not 0. The minimum of it is the smallest K you can find with ger K not equal to 0. So I was a little bit panicked a moment ago. Right, so I said orientable, so what does it mean? So to be orientable means that the top and lowest graded pieces have rank 1. Okay, and the orientation is you just pick a choice of generators, like 1 and 1 dual, like I was using before. And then, so the last part of this is if F and W is oriented, then the height of FW is just equal to delta minus R, 1 over 1 dual, where R is max minus min over 2. So in other words, these pieces have rank 1, so one of them has to be type AA, the other one has to be type BB. These are both, this is the top, this is the bottom, and then delta minus R is just the piece from the top to the bottom. Okay, so as long as we have an oriented by extension, sorry, an oriented mixed Hodge structure, we can define the height in this way. So, okay, so good. So now I'm going to kind of state the main theorem with Burgos Gil, and Zuvik. Okay, so we're going to let X be a smooth projective variety over C, dimension D. We're going to take classes in ZP and ZQ. So these will D of Y and D of Z be 0. So these will give us classes in the higher child groups. And I'm going to put on this condition, just like we had before, that 2p plus q minus d minus 1 is m plus 1. And I'm going to require that they intersect properly. But I'm not going to say anything about their real regulators have to be equal to 0. Because I want to be able to move my cycle in families, and I can't do that if I make this requirement about the real regulator having to be 0. Okay. So I guess for classical cycles, that regulator equals 0 thing is kind of automatic, because if you have R of 0 and something like -1, that always splits over R. But okay, so then what? So A, there is whatever canonical associated functorial mixed odd structure. Mixed odd structure B of Y, Z with weight graded quotients. So GER W0 is Z or Z1. GER W -2 and GER W -4. So that's Z of this one dual. And now we are at the end of the screen. And B, if we define Y of ZW to be the height of BYZ, then this height I'm defining in terms of this mixed Hodge structure, BYZ, is equal to this Archimedean piece that was defined by Subic and Jose whenever the real regulator of Y is equal to the real regulator of Z is equal to 0. Okay, so in other words, this construction is a generalization of what Subic and Jose had constructed previously for their Archimedean part of the height in some arithmetic setting. Okay, so now in families, if we apply this construction in families, we'll get an admissible variation of mixed Hodge structures over some Zariski open. I'm definitely not going to have time to say anything about that, except for the fact that, in a sense, all of these constructions are of geometric origin once you write out all of the details, which I'm not going to do in this talk, but these things do give rise to admissible variations over some Zariski open set. Okay, questions? Okay. All right, so now I want to emphasize the following key point. So for the ordinary height pairing, the cycles have disjoint support. They don't intersect. Okay, for higher cycles, you only get to assume proper intersection, and that intersection is going to be most likely not empty. Okay, that's one of the big issues. Okay, so when M is equal to N is equal to 1, then these intersections is a finite number of points. Okay. Okay, so and so in this case, this B of Y Z has a contribution to GER W -2 from the cohomology of X in the right degree and this finite set of points. Okay. All right, so now I want to explain to you why this is so absolutely critical. Okay, because this caused certainly me confusion for many years. Okay, So horizontality says this Hodge filtration that we have to construct, it has to satisfy FP differentiates to be in FP minus 1. So now for ordinary cycles, this is really good. Because we have z of 0, we have z of 1, we have this GER W minus 1. This part is fixed by nu A, this part is fixed by nu B. Our O star action is going from z of 0 down to z of 1. That's horizontal. Okay, that's good. We can have nice horizontal deformations. Okay, so the naive view, the kind of incorrect view, but what you might think happens for higher cycles is that, okay, we have z of 0, we have this h, and we have this z of 2. So this is fixed by this kind of higher normal function nu A. This is fixed by this higher normal function nu B. And okay, so then the only thing left to do is go down from here to here, right? Some torus are here, but this is not horizontal. So if you want to glue normal functions, higher normal functions, as soon as the difference between the weight here and here and here and here, so that's bigger than 1, this is going to be locally rigid. So that would mean that your height that you were going to construct would be something which is going to be locally constant. Okay. But this view here, this is actually incorrect. Okay. So, okay, so what's the correct, what actually happens when we're gluing together these higher cycles? Okay, what happens is we have our we have our higher normal function here. It's z of 0 to h. It's fixed. And we have h down to z of 2 here. It's fixed. Because you have those extra set of points, what happens is, well, you're going to get what you had before. Okay, but you have to add in some z1 to the r's. And the higher normal function only tells you, it only fixes this part and this part. It doesn't tell you anything about from here to here and here to here. And this part over here is z of 0 to z of 1, that's horizontal. Z of 1, this is z of 2, sorry. Z of 2, that is horizontal. Okay, so having those extra points is absolutely critical to the fact that we actually are going to get some interesting functions out of doing this. And so I should say about that m plus, our restriction on m plus n, I mean, in general, what we expect is, I mean, we'll be having some nu A here and some nu B here, and we're going to glue them together, but our condition on m plus n being equal to 2, that was what was giving us just points, right? In general, this outermost right here, these will be 0, but otherwise we're just going to get whatever can fit in the rest of the Hodge subdiamond. So that's what we expect the general picture to be. And so now maybe I will say a little bit more. Okay, so obviously m plus n has to be even because I put 2p plus q minus d on the other side of it. So this is 4. Okay, so we think that we can do it up to 4 without too much trouble. So let's see what that would give. Well, we already kind of discussed 2. So for threefold, we're going to be taking 2 classes in Z3, X2, and then in this special particular complex. Okay, so then what do we have? We'll have 0, 0. We get 0 here, we get 0 here. So we'll have a -1 part here, our weight 3 part from our threefold, plus possibly something else, and these other pieces down here. So now this exactly looks like what Patrick and I were studying earlier, with one small exception. I actually don't know what the ranks of the -1 and the 2 parts are, but okay, x1 of A by B is equal to x1 of Z of 0 by a dual tensor B. So I mean, modulo a little bit of trickery, I can think of these 2 things as coming from normal functions. So then, as I was saying, in this context, we'll be getting these by extension line bundles coming out of, if I were to do this construction for threefolds in a family, I would again get these by extension line bundles, and we could consider singularities, et cetera, et cetera. So that's that part of it. And now, okay. Not the other part. So now we have to look at the asymptotic behavior. So as long as we're just looking at an oriented by extension over S, we can consider its height, and we don't really need any, we don't need it to be coming from some height pairing type of story. Okay, so we're going to let S be a Zariski open subset in some S bar. D is the complement, is a normal crossing divisor. Now I'm going to look at the Hodge-Tate case. I want oriented Hodge-Tate variation, and now I'm going to assume that the difference between the top and the bottom weights is at least 4. Okay, so then I want to assume that this is S, this is V, is admissible with respect to S bar, and it has unipode model. It's the Hodge-Tate case, so it's actually not, I don't have to actually write that, but it has unipode monotomy about B, and so then the limit mixed Hodge structure is of Hodge-Tate type at some point P in D. And so what we prove is that the limit as S goes to P of the height of the variation as I define it above is actually equal to the height of that limit at P. So that's kind of like the analog of what was in that result with Patrick. And I should say it's kind of implicit in here that, why is this thing so off angle? Okay, so implicit here is that when the difference is greater than or equal to 4, this height doesn't actually see this change in the limit Hodge filtration going from F infinity to e to the n F infinity. Okay, so that's so those, I guess I think I've stated some of the main results of the paper now. So this would be a good place to stop for questions, because after this comes some examples, and after that, in the unlikely event there's any time, comes some a little bit of discussion of the proof. So, questions? once, twice, 3 times. Okay. So now for something that'll be a little bit different. I gave this talk a while ago, and for some reason, their video equipment did not like. Anyway, that was a problem. Okay, so now, yeah, so I gave this talk a while ago. Their video equipment, for whatever reason, did not like things to be. What? Okay. All right. Okay, so here we're going to do some examples now. So the geometric example will be the last one. But just to prove to you that that theorem that I just said isn't a totally crazy theorem, because you might be saying, well, it's a variation of Hodge structure and degenerates, so therefore that height function has to be degenerate, and that actually is not true. Okay, so one of the basic examples of a variation over P1 minus 3 points is the dilogarithm variation. And so in this case, the height of V is actually minus the Bloch-Wigner dilogarithm. And so, I mean, this computation is, I mean, there's nothing to it. So, I mean, we just have to write out an explicit description of the dilogarithm variation. So there's one where we take our basis of the IAA and the limit to BC minus, sorry, not in the limit, to BC E minus A. And then this is the lattice. So you can either trivialize the lattice, or you can trivialize the Hodge filtration here. It's the Hodge filtration that's being trivialized, and the lattice is moving around. And now to actually compute is just grind away at the linear algebra. So anyway, so for the dilogarithm variation, you do see explicitly what I had said before, that it really does extend and it doesn't have singularities at 0, 1, and infinity. And I should point out, so this is something, maybe I can zoom in a little bit, make it a little bit easier on the eyes. That's a little bit better. Okay. In fact, Zagier and others, they've attached kind of single-valued versions of the polylogarithm to polylog variations, and it's either get a graduate student to do this or sit down and compute for a few weeks. But I mean, I think if you take the polylogarithm variation and you compute this height, you're going to see that this height is some linear combination of the ones that Zagier and others define. So that's the simple example there. Okay, so our next example is from a nilpotent orbit. And so, okay, so I've always been talking about, I mean, I stated my result for Hodge-Tate things, and I said it extended. Okay, so now I should show you that there's a reason that I restricted it to Hodge-Tate, and it wasn't because I'm being lazy. Okay, so so we're going to take now an example that's, if you'd like, kind of twisting an elliptic curve. So it's I0, 0, I minus 2 minus 1, I minus 1 minus 2, and I minus 3 minus 3 on the interior over the disk. So I'm going to look at the nilpotent orbit attached to that. So I'm going to assume its limit is Hodge-Tate in cubed is non-zero. Okay, so if, and then, okay, so there's an explicit, okay, so the point of this example is just to say that, you know, I wasn't being lazy, right? Okay, so I said it extended for the Hodge-Tate one, and then there's a reason for that, okay? So this is what I would, do you hear me now? Yes?
Yeah, I hear you, yeah.
Okay. Okay, so this is kind of like the twisted elliptic curve, right? So now we're down to weight minus 3. Okay, so we consider the generation to a Hodge-Tate case with n cubed is non-zero, and we just look at a nilpotent orbit. Okay, so this is the data for this example, and I think it's very important, except that I want to say that in this case, the height behaves more like what you might expect, right? It's some constant, okay, and so, you know, you might want the pi over cubed is also kind of natural in this context. Okay, so it's a constant times the log of the parameter here, which is kind of maybe more what you would expect. Okay, so all right, so if you're not Hodge-Tate, then you don't have this property that it just extends. I mean, that's the content of this example. And now, okay, we are not going to discuss higher child groups. Okay, so now I think the last thing that I want to do, let's make sure we get to the punchline. Okay, no, I'll just do this whole thing. I think I have enough time for it. Okay. Okay, so now I would actually like to do quote unquote triangles in P2. So this is maybe like the simplest example of some higher cycles. So we're going to take X is P2, homogeneous coordinates, X0, X1, and X2. So S0, S1, S2, and these X0, these are all linear sections. Okay, so Li, that's the divisor of Si, Li prime is the divisor of Xi. So these are just going to give us 6 lines in general position. And so I'm trying to construct a higher child cycle, so I need to give you some functions, and the obvious way to take those functions is by taking the ratios of those linear sections. Okay, so for alpha and beta and C star, I can cook up this higher child cycle. So L0, that's the divisor of L0. F0 is this function, which would be what, S1 over S2, et cetera, et cetera. And then I have to subtract off something coming from the points in order to get proper cycles. Okay, so these two cycles are in Z1 of P2, comma 1. So these are the triangles. Okay, so then I would like to calculate the height pairing between these two cycles. And how do I do it? Okay, so I can write my section S0, S1, and S2. These are A0, X0, A1, X1, A2, X2, et cetera, et cetera. Okay, so the height pairing between these two cycles has a very natural description. So so this is a sum with 9 terms. So I have to take all the cyclic permutations of 0, 1, and 2, and I have to take all the cyclic permutations of A, B, and C. So in this term here, I get to act by permutations on both the A and the B, and I get to act on the indices. So this gives me a 9-term sum. So in this particular case, this height pairing is given by this 9-term sum of dilogarithms. So so maybe that's not too unexpected, but it is showing you that this this height pairing does produce kind of interesting functions, if you'd like. And I think the next slide is the construction of that complex, but I think I should quit while I'm ahead and not say anything about that. But so questions? I think that's enough for now. Okay, I go back to the screen. All right, questions or?
I'm trying to think. I'm trying to think of a question. I mean, the thing that's still a tiny bit confusing to me is when, I mean, you were saying these higher height pairings are rigid, but then somehow they're
Okay,
not.
I can explain that.
They're not.
They're not
the duality between the rigid and the not rigid.
Okay, what I was saying there, that's a good question. Okay, so let me see. Okay. Make sure we get. Okay. All right. So what I was saying, the thing that confused me for a long time. Okay, here we go. Here's the slide I'm looking for. Okay, am I still sharing the screen?
Well, you got the desk, but yeah, that's a nice desk, by the way.
Okay. Okay. So what I was saying is that so by horizontality, so FP has to go in. So I have to construct horizontal deformations. So from ordinary cycles, I just have this O star action, right? It goes from Z of 0 to Z of 1, and it's horizontal, and I can deform things easily, right? If I were to take higher cycles, right? Once I fix this extension from Z of 0 to weight -2, and this extension from weight -2 to weight -4, right? The only thing that's left for me to do is mess with the extension from Z of 0 to Z of 2.
Yeah.
But that is locally rigid, right?
Yeah. Yeah.
Okay, so if I try and glue two normal functions together, so here I can glue normal functions together, great, I get a line bundle, right? Here, I'm in trouble, right? Because it would be locally rigid. Now, maybe you like the height to be locally rigid or whatever, but okay. So what I'm saying is, in actuality, what happens is that, okay, so I have these two normal functions, right, that I'm trying to glue together, but when I glue them together, these cycles only intersect properly, right? So it's just, it just happens to be a fact that for the usual Archimedean case with ordinary Chow cycles, that meant not intersecting. For higher cycles, right, they actually do intersect, and there's no way for me to avoid making them intersect. So that means I have to add not only the part that came from the cohomology of my variety in the right degree, but a bunch of extra terms which came from the points, right? So this part is fixed, right? And this part is fixed by the higher normal function, right? But this part here, I don't have any, I don't know anything about like the extension from here to here or here to here. So I get to move this part.
Oh, so that gives you, but those gives you a bunch of like C stars or whatever. So look at X1 of Z by Z1. They just give you a bunch of C stars that are.
Or O stars. So then,
O stars, yeah, O star. I meant O stars, but you know what I mean.
Yeah, right. So I'm saying, so there wouldn't.
Yeah.
So what I was saying is, we're always trying, we were making good with the fact that we had like a line bundle, right? So if you like, I mean, this extra piece would be some kind of vector bundle, right? From these two pieces. So what actually happens is I get, an extension. I get to deform it by deforming this part of the extension. So that is horizontal. So
yeah, it winds up being a bunch of O stars, essentially.
Yeah, okay, so I get vector bundles, yes? So, okay, that's fine. Yes.
Yeah.
And that, again, right? So I was saying, so in general, you know, what's going to happen is I'm going to take these two higher normal functions and I'm going to like glue them together, right? And I'm only going to get a proper intersection. And all I'll be able to do with that proper intersection is I can control the level of the Hodge structures to make sure it only appears kind of like on the interior part of these, right? So for example, with the with the one I was talking about, right? I mean, I had the 0, 0, right? Then okay, I have -2, 0. Then I get to add some stuff in -1, 1, right?
Mm-hmm.
And then I get to add a little bit of stuff in 0 minus. Okay, so this part I don't mess with this part, but here I get to mess with stuff, right? Because I have this C1 factor. And then down here I also get to, okay. So the extra part here comes from intersecting points, which gives me classes in here. And then for that next example, where was it? Okay, so the next example that I had, right, with the three folds, I mean, I'll get something in here and then some extra stuff here, right? So in the three folds, again, I don't know what the rank of, so I'm trying to say I really needed that Hodge subdiamond to get me horizontality, right? Because without
You really need the
-1,
-1, and the -2 parts.
Yeah, so I really do get horizontal here, and I get horizontal here, right? And of course, I also get horizontal down to these two pieces, right? So I really actually need that horizontality to actually be able to have interesting deformations and get interesting heights. And then what I was saying here is that I don't know what the ranks of these two pieces are, but I can use that usual extract to, I could really make this part here into a line bundle like the part that we were thinking about when we were doing the by extension line bundles. So I don't know what the significance of singularities would mean in that context, or if there are singularities in those contexts.
Yep. Cool.
Okay, so that's
Other questions? If not, let's thank Greg for the wonderful talk.